Hey there. It's fantastic to have you back with us on Wonderscope, where we break down the mind-blowing mysteries of space and time. Now, you might have heard a lot about black holes, but do you really know how deep these cosmic giants go? Today, we're diving into how scientists have found a new way to look inside black holes. Trust me, it's not as impossible as it sounds. Black holes have fascinated scientists for over a century. It all started in 1915 when Albert Einstein dropped a bombshell with his theory of general relativity. He predicted that the fabric of space-time could collapse into an object so dense that nothing could escape it, not even light. This idea was as wild as it sounds, and for decades, black holes were relegated to the realm of theory. But guess what? Einstein was right, and over time, scientists started gathering evidence that black holes weren't just theoretical, they were real. But before they were known as black holes, physicists had another name for them. Back in the early 20th century, they called them gravitationally collapsed objects. Catchy, right? It wasn't until the early 1960s that the term black hole came into popular use. In 1963, and Ewing, a science reporter for Life and Science magazine, used it in an article. The term quickly gained traction, but it wasn't until a 1967 lecture by John Archibald Wheeler, a renowned American physicist, that the name stuck. Wheeler not only helped popularize the term, but made it iconic. He realized that black hole had a certain pop to it, don't you think? But, hey, just because scientists came up with the term doesn't mean they immediately had evidence of these monsters. That didn't happen until 1964, when astronomers observed something strange in the binary star system Cygnus X1, a system about 7,300 light-years away from Earth. This system included a massive blue supergiant star weighing 33 times the mass of our Sun and an invisible companion with about 21 times the mass of the Sun. That invisible companion was, you guessed it, a black hole. What made this discovery so mind-boggling was the presence of X-rays that were being emitted from the region around the black hole, not from the black hole itself. That would be impossible since nothing can escape from inside. These X-rays were coming from the accretion disk, a hot, swirling mass of gas and dust being pulled in by the black hole's powerful gravity. This discovery sparked a cascade of new evidence suggesting that black holes were real, from gravitational waves shaking the very fabric of space-time to the detection of stars moving in ways that could only be explained by the presence of an invisible mass. Speaking of mysterious movements, have you ever wondered how black holes affect their surroundings? It's like a cosmic game of chess. The gravitational influence of black holes disturbs the stars around them, causing some to orbit at incredible speeds. And get this, when a star ventures too close to a supermassive black hole, it faces an unfortunate fate known as spaghettification, getting stretched out into a long, thin strand like spaghetti. Sounds a bit dramatic, right? Now, here's the kicker. Despite all these discoveries, some skeptics still doubted the existence of black holes. They wanted proof. I mean, if these things are real, why don't we have a picture of one? Well, in 2019, that's exactly what happened. For the first time ever, M87 star, a supermassive black hole at the center of the Messier 87 galaxy, about 55 million light-years away, was photographed. This was a huge breakthrough, a historic moment in astronomy. The image was captured by the Event Horizon Telescope, EHT, a global network of 8 radio telescopes that work together to create an Earth-sized virtual telescope. Think about that for a second. 8 telescopes, thousands of kilometers apart, all pointing at the same spot in space, working as one. It's like a global team of astronomers having a massive virtual telescope session. And what did they capture? A glowing ring surrounding a dark center, which is the event horizon, the boundary beyond which nothing can escape. The size of M87 star is staggering. It weighs about 6.5 billion suns. For comparison, our own supermassive black hole, Sagittarius A star, weighs only around 4 million suns. The event horizon of M87 star is about 40 billion kilometers across, which is nearly 267 times the distance from the Earth to the Sun. To help you picture that, think of 37 hours of light traveling from one side to the other. Yeah, it's that big. This image was published on April 10th, 2019, and it's mind-blowing. It proved black holes weren't just theoretical, they were real, and we could now see them. But wait, the story doesn't end there. The EHD didn't stop after photographing M87 star. In March 2021, they released a new image of M87 star, this time in polarized light, revealing how magnetic fields work around the black hole. Cool, right? But the EHD team didn't just stop at M87 star. In May 2022, they released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy, the Milky Way. Unlike M87 star, Sagittarius A star is smaller and lighter, which made it harder to capture. But the team pulled it off. They used the same data they collected back in 2017 to create an image of Sagittarius A star, and boom, it became the second black hole in the universe to have an official image. These images are more than just cool pictures. They're proof that modern astronomy is on the right track, confirming theories of general relativity and giving us new insights into how black holes work. But here's the thing. Even though we've got these incredible images, we're still looking at the very edge of the black hole, the event horizon. That's the closest we can get. It's like trying to peek inside a locked treasure chest, but only seeing the shiny exterior. So, how do we get a glimpse of what's going on inside the black hole? Well, scientists are getting creative. They're focusing on something called the photon ring. Now, hold on. Don't get confused by the name. It's not some ring inside the black hole itself. If it were inside, we wouldn't be able to see it at all. Instead, this ring is located just outside the event horizon, the point of no return, where light can't escape the black hole's powerful gravitational grip. What you're actually seeing in images of black holes is something called the black hole shadow, a dark region formed by the warping of space-time around the event horizon. The shadow has a diameter about twice the size of the event horizon. You can think of it like a massive gravitational lens distorting the light that comes too close. Now, here's where it gets interesting. When light, or photons, gets close to a black hole, they experience some wild stuff. Some photons get sucked in, crossing the event horizon, never to be seen again. Others are just bent by the black hole's gravity and continue on their way. But there's a sweet spot. Some photons find themselves in a strange gravitational dance. They circle the black hole once, twice, maybe even 3 times before they escape, or in some cases, they can circle the black hole forever. This is where the photon ring comes into play. It's the collection of these photons in orbit around the black hole. Imagine it like this. The photon ring acts as a cosmic movie camera, capturing light from all directions, all around the black hole, in what seems like an eternal loop. It's been called an infinite light trap. Now, why does this matter? Well, photons in the photon ring essentially reflect the universe back to us in a way we've never seen before. As they circle the black hole, they don't just show us the black hole. They show us distant stars, galaxies, and cosmic objects, potentially multiple times. So, if scientists could somehow photograph this photon ring, imagine a movie reel of the entire universe, with light looping around and showing us different versions of the same galaxies and stars. How cool is that? But wait, there's more. Until recently, the photon ring wasn't taken very seriously by scientists. The focus was always on the event horizon, the ultimate boundary where nothing, not even light, can escape. Modern physics has long stated that any matter or energy passing through this point gets lost forever. We could never see or retrieve any information about what happens inside the event horizon. That's why we've never been able to answer questions about the black hole's interior. It's like staring at the outside of a treasure chest, knowing there's something inside, but being totally unable to peek. The event horizon is the boundary where the laws of physics, as we know them, break down. But, as it turns out, the photon ring might just hold the key to unlocking what's going on behind that boundary. You see, recent theories suggest that the photon ring could carry information about the quantum structure of the black hole. Pretty wild, right? Back in May 2022, a team of researchers led by Andrew Strominger from Harvard University published an intriguing study on the photon ring. They found that the photon ring has a special kind of symmetry that helps it maintain its shape, even if it gets deformed by external forces. This discovery raised some eyebrows in the scientific community. What if, instead of just reflecting light, the photon ring acts as a kind of mirror to the black hole's inner workings? Some researchers are now debating whether the photon ring could give us a 3-dimensional look at the interior of a black hole, something we never thought possible. Let that sink in for a second. What if, by decoding the photon ring, we could finally see what's going on inside a black hole beyond the event horizon? If that turns out to be true, we could shatter some of the most fundamental boundaries of physics that have existed for decades. It might even allow us to peek inside the black hole's singularity, that mysterious point of infinite density where all known laws of physics collapse. Now that's a game changer. But before you get too carried away with excitement, we have to talk about the black holes themselves. Here's the thing. Most black holes in the universe are small compared to the supermassive ones we've been studying. The two black holes we've been able to photograph, M87 star and Sagittarius A star, are the giants of the black hole world. M87 star is about 53.5 million light-years away, while Sagittarius A star is a mere 26,673 light-years away from us. But even though Sagittarius A star is much closer, it's actually much smaller and lighter than M87 star, making it harder to capture in sharp detail. You might think that being closer to Sagittarius A star would make it easier to study, but there's a catch. Because it's smaller, the material in the accretion disk, the swirling mass of gas and dust around the black hole, moves much faster. For the bigger black holes like M87 star, the material takes days, even weeks, to make a full revolution. But for Sagittarius A star, it only takes minutes to hours, which means capturing a sharp image is like trying to take a picture of a hyperactive toddler running around at night. It's super tricky. And on top of that, there are massive clouds of dust and gas in between Earth and the center of our galaxy, which distort the signals we're receiving. So, it's like trying to take a picture through a foggy window. But despite the challenges, we've managed to make incredible strides in capturing these elusive images. And we've learned a lot about how black holes work. For example, the material around a black hole doesn't just fall straight in. It gets funneled toward the poles by powerful magnetic fields, where it's blasted out in high-speed jets. These jets can extend across millions of light-years into space, and they emit high-energy radiation, like the gamma-ray flare we mentioned earlier. This flare from M87 star in 2018 gave scientists a rare opportunity to study the dynamics of these jets and learn more about the structure surrounding black holes. Now, back to the photon ring. The thing is, we're still a long way from fully understanding what it could reveal. But this is where things get really exciting. If we can decode the photon ring, it could provide us with crucial insights into how black holes function on a quantum level, and possibly even give us a window into the mysterious heart of the black hole itself. So, let's circle back to our main question. Can the photon ring show us inside a black hole? Well, we don't know for sure yet, but the research is progressing, and it's opening up some incredible possibilities. And that's just the beginning. Scientists are continuing to study the photon ring, and who knows, maybe in the not-so-distant future, we'll be able to decode it and finally answer some of the most profound questions about the universe. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell to stay updated with WonderScope. Thanks for watching, and we'll see you in the next video.